Focus input motor.
Hello, hello. চল সবাই এসে গেছে। কারোর কোথাও প্রবলেম আছে? এনি প্রবলেম? ইউ হ্যাভ বট এনিথিং?
না স্যার।
লিখেছিস তুই সংস্কৃতা?
হ্যাঁ।
ক্লাস করার কি দরকার? তাহলে প্রতিদিন ভিডিও লেকচার করে একটা পাঠিয়ে দিলেই হয়ে যায়, এত সুন্দর বোঝা যাবে। আদিত্য, এনি প্রবলেম? নো স্যার। আদিত্য, আদিত্য কোনো প্রবলেম আছে? তো মাইক্রোফোন কাজ করছে না। দৃশ্য?
নো স্যার।
রিজুলা?
নো স্যার।
আদিত্য আছিস না নেই রে? তো কাজ করছে না তো সাউন্ড। রিলক কর, রিলক কর, রিলক কর। শুরু করি। What we are going to do today is we are going to start with gas laws. But before I start with gas laws, let me just give you a brief introduction about dipole moments, which you have already discussed a little bit on the last day. Today, we are just going to build up on that. We are not going to do any problems of dipole moment. I'm just going to give you the concept of dipole moment. So what I'm going to explain is the concept of dipole moment. Now, dipole moment is expressed as mu, right? That is the way, that is a symbol we use for dipole moment. Now, what happens is like this. Suppose I have got a molecule consisting of A and B atoms. And suppose this A has got an electronegativity of 2.5 and B has got an electronegativity of 3. Suppose. That means B has got electronegativity of 3, which is more than the electronegativity of 2A, that is 2.5. Now, how do you define electronegativity? You have defined electronegativity as a tendency of an atom to withdraw the bonded pair of electrons towards itself. Right? Now, this is the bonded pair of electrons. You have this. If you have a bonded pair of electrons like this, then B is going to withdraw this bonded pair of electrons towards itself. That means under these circumstances, some of the electrons which originally belonged to A has now gone to B. So A will be electron deficient and B will be electron rich. But a complete charge is not taking place. Only a small portion of that charge is being withdrawn from that covalent bond towards B. Therefore, you call this as delta minus and you call this as delta plus. So this delta minus and delta plus magnitudes have to be the same. Their magnitudes have to be the same because whatever B has withdrawn, A has lost. Whatever B has withdrawn, A has lost because only A and B have got electrons. A is giving 1 electron, B is giving 1 electron. Now, if B is withdrawing a portion of the electrons of A, thereby becoming delta minus, A definitely has to be delta plus. So delta minus is equal to delta plus, only the charges are different. So under these circumstances, we have got a positive center and we have got a negative center. And they are separated by the bond length. That means what I can do is this, I can write down out here delta plus and I can write out here delta minus, and they are separated by a distance d. And they are separated by a distance d. So we define dipole moment as the charge separation, that is delta plus or delta minus, you can do it anything, right, into the distance of separation, that is d. So this is how you define the dipole moment. If there is complete charge separation, say for example, in the case of compound like this, there is a complete charge separation. That means A is unit positive and B is unit negative. Then you can define mu as the charge into the distance of separation. So this is how you define the magnitude of dipole moment. So this is how you define.
1 second, sir. Magnitude 1.
Yeah, okay. What happened? बोलो ऋषभ, where are you?
Yes, sir. Sir, sound कट गया, sir. एक बार वापस बता दीजिए ना ये magnitude वाला.
Yeah. Nothing. The magnitude of the dipole moment is given by the charge. This plus and minus has to be the same. Did you understand this?
Yes, sir.
So it is the product of the charge into the distance of separation between these two charges. This is what is given by the magnitude. But
Yes, sir.
dipole moment is also a vector. It is a vector. Vector means it has got both direction as well as magnitude. So I found out the magnitude. What about the direction? The direction is taken like this. It goes from the positive center towards the negative center. This is the direction of the dipole moment. Right? Suppose, say for example, I have got ammonia out here. Right? I have got ammonia out here. So I've got 3 bonds of nitrogen, hydrogen. Now, electronegativity of nitrogen is, say, for example, 3, and hydrogen is 2.2. That means this bonded pair of electrons will be withdrawn by the nitrogen in all these 3 cases. That is for each one of them, this will be delta minus and this will be delta plus. And then you have got a bond length. So the charge, so what will be the magnitude? Magnitude will be delta plus or delta minus, whatever is the charge, right? Into the distance of separation, that is the bond length. That will give you the magnitude. And what about the direction? The direction will be from the positive center towards the negative center. So in this case, it will be like this. From this is the positive center, this is the negative center. Like this. Suppose you have got CCl4. Suppose. Then what happens? This will be my delta plus. This is the electronegativity value is 2.5. The electronegativity value of chlorine is 3.2. Therefore, the electrons will be withdrawn in this particular direction. So out here, what is going to happen? It will be essentially delta minus. This will be carbon will be delta plus. Now, what will be the structure of CCl4? Okay, let me go back to the basic principles. Carbon has got 4 valence electrons. Chlorine has got 7 valence electrons. And there are 4 chlorines. So 28. So that makes 32. You divide it by 8 to get the hybridization. That means I have got 4 bond pairs and 0 lone pairs. That means this is sp3 hybridization. If this is sp3 hybridization, then this will be tetrahedral. That means I have got carbon out here. I have got chlorine out here. I have got chlorine out here. I have got chlorine out here. And I have got chlorine out here. So what will be the direction of the dipole moment? First of all, this will be all be delta minus. So my dipole moment will be having a direction in this direction, in this direction, in this direction, and in this direction. Now, this for all of this, you need to do vector addition. And when you do vector addition, you'll find out that mu is equal to 0. That means there will be no dipole moment. So this is how what we mean by dipole moment. Whenever a particular entity has got equal charge separated by a distance, then there will be a dipole. Dipole means dipole. Dipole essentially means what? Dipole essentially means you have got di. Di means 2. Di means essentially 2. And pole means this is my 2 charges. One is plus and one is minus. That means 2 poles. So this is how we call it as a dipole. That's why we call it a dipole. And dipole moment is the magnitude. And the direction is from positive to negative. This is what a dipole moment is all about. This is a very basic idea. I'll talk about dipole moment. It's essentially, I'm going to discuss a full lecture on dipole moment because there are a lot of problems that come from dipole moment in chemical bonding chapter. And you will be requiring the concept of dipole moment throughout, but somebody told me that gas laws has to be done, so I'm doing it. Otherwise, I would have loved to do dipole moment today itself. Because many questions comes from dipole moment. Sure. So that is what dipole moment is all about. Right. Now what we are going to do is, we are going to talk about gas laws. So we are going to start with gas laws. Now, in order to understand gas laws, you have to first of all understand the intermolecular forces. What are the intermolecular forces that actually operate between molecules? Right. Once we understand these intermolecular forces, the kinds of intermolecular forces, the origin of the intermolecular forces, the parameters upon which these intermolecular forces depends upon. Once we discuss about those, we'll define what our ideal gas is. And when we talk about ideal gas, we are going to talk about 4 laws. The Charles law, the Boyle's law, the Gay-Lussac's law, and the Avogadro's law. These are very simple laws. These are all experimental laws, which are applicable for ideal gases. We'll understand what ideal gases are. Now, once we have understood the ideal gases, we'll go and we'll consider these intermolecular interactions that we are discussing today and differentiate between an ideal gas and a real gas. And whenever we talk about real gases, we are going to talk about liquefaction of gases and all those graphs, other things. So the first half of this discussion is rather easy. I don't think that you require a teacher to at least understand the first half. Of course, as far as the diagrams are concerned, it requires a little bit of practice. But you require a teacher's help only in the last 2 portions. That is the kinetic theory of gases and real gases, the van der Waals gases. Those are the only 2 things that you require a teacher to understand. But anyway, I'm going to explain from the very beginning. First of all, what we are going to do is this. We are going to understand what are intermolecular forces. Now, intermolecular means what? I have got a molecule out here and I have got another molecule out here. That means 2 different molecules, interstate competition. What does it mean? Punjab is fighting against Bengal. So it's an interstate cricket competition. Inter means 2 different entities. So inter means 2 different entities, whereas intra means same entity. So you have got 2 concepts out here, inter and intra. We are not going to discuss about intra today. We are essentially going to talk about inter. So intermolecular, that means I have got 1 molecule A out here. I've got 1 molecule B out here. We are going to talk about the interactions that takes place between A molecule and B molecule. They might be the same molecule. So for example, I've got hydrogen gas. So I've got a hydrogen molecule out here. I've got a hydrogen molecule out here. What kind of interaction takes place between these 2 molecules? Those interactions comes under the purview of intermolecular forces. So I've explained what are intermolecular forces, right? Fine. Now, what we are going to do first is we are going to talk about 3 different kinds of forces that actually takes place. One of them is called as dispersion forces or London forces. These are big names, very simple to understand. One of them are called as dispersion forces or London forces. Right? Now, what we are going to do is this. We are going to talk about, say, for example, I take 2 molecules out here, right? I take 2 non-polar molecules. I take 2 non-polar molecules. Now you will immediately ask, what do you mean by a polar molecule and a non-polar molecules? Polar comes from the word dipole. So if a molecule possesses a dipole, if a molecule have a dipole within it, you will call it as a polar molecule. Say, for example, HCl. HCl is a covalent compound. The electronegativity value is 2.2 for hydrogen. For chlorine, it is 3.5, 3.2. So this will be delta negative, this will be delta positive. And the direction of the dipole will be from positive to negative. So this will be my dipolar direction. So this is a polar molecule. Whereas, say for example, I take hydrogen, or say for example, I take oxygen. Now, out here it is also 2.2, out here also is 2.2. This is 3.5, this is 3.5. So there is no question of charge separation. Just like that. Apparently, there's no question of charge separation because the electronegativity values are the same. Under these conditions, if there is no charge separation, then you will call these molecules as non-polar molecules. You call these molecules as non-polar molecules. And we are going to talk about the interactions that can take place in non-polar molecules. And whenever we talk about the interaction that takes place for non-polar molecules, we call it as dispersion forces or London forces. He said London is basically a name of a scientist. He first basically proposed this concept, and therefore the name London forces came into picture. Now, what happens, say for example, in the case of London forces? Now, what you have, essentially, what you have is you have got a nucleus. You have got a nucleus. And surrounding the nucleus, you have got an electron cloud. Suppose I have got this particular molecule. Suppose, right? I have got, once again, another molecule out here. I have got another molecule out here. Right? I've got another molecule out here. And this is its electron cloud. And this is its electron cloud. This is its electron cloud. Now I've got two molecules out here. And they are non-polar. That means there is no dipoles within this particular molecule. But it has also got an electronic cloud out here. Now, what happens is this, when these two molecules actually come closer with one another, then out here, this is my electron cloud. I've got negative charge out here. I've got negative charge out here. So in this case, when the two molecules are coming close to one another, then what's happening? Essentially, this negative charge is going to repel this particular negative charge. As a result, what's going to happen is this, there will be the case of fluctuating dipoles. When they're coming together, and suppose this negative charge starts to influence this negative charge, then what happens is this, this negative charge is going to push this particular electron in the opposite direction, right? This particular electron is going to push this particular electron. That means what's going to happen is this, from here, let me move into this particular direction. Now what you are going to have is this, you have got this particular molecule, shape will be like this. The shape will go like this. So this electron cloud has come in this particular direction, and this electron cloud has increased. So what's going to happen is this, the electron in this particular molecule will go away from that particular thing. So it will go away in this particular direction. That means out here, this will be minus, and out here, the electron has moved into this particular direction because electron repels. So in this case, it would be plus. So this becomes minus and this becomes plus. So there will be an attractive interaction between these two. This is happening. Why? Why this is happening? Because the electron clouds are momentarily shifting in this particular direction. In the next instance, the opposite thing might happen. This particular electron cloud will come into this particular direction. So this will become negative and this will become positive. So when this kind of interaction takes place, that means essentially due to fluctuating dipoles, you call that kind of an interaction to be London forces. So there will be an attraction. So there will be an attraction between these two molecules due to fluctuating dipoles, and you will call them as London forces. Clear? And when you call this as London forces, that means it has been observed that this attraction is proportional to 1 by r to the power 6. Now, what does one attraction proportional to 1 to the power 6 means? Essentially means if these molecules get separated a little bit, it's inversely proportional, right? Attraction is proportional to 1 by r6. Means what? Means what is this? That as the distance increases, the attraction decreases. Inversely proportional. That's the meaning of the word inversely proportional. As the distance between these two molecules increases, the attraction decreases. By how much? R to the power 6. That means I can write down, for your understanding sake, for the clarity sake, I can write down attraction is like this: 1 by r into 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 1 by r. So what does it mean? This is R6. If I decrease the distance a little bit, then the attraction, if I decrease the attraction is going to increase. How far it is going to increase? It is going to increase very much by par to the power r to the power 6. If I decrease the distance, if I increase the distance a little bit, first of all, I was decreasing. Right now, if I increase the distance a little bit, what happens? The attractive force is going to decrease. If the attractive force is going to decrease, by how much? R to the power 6. That means a little bit of distance is going to make a hell lot of difference. A little bit of difference in the distance between these two molecules is going to make a hell lot of difference in terms of attractive forces. That means if the molecules is a little bit away from each other, the attractive forces will essentially vanish. That means there will be no attraction at all. So these forces are therefore called as short range forces. Short range forces. And varies as 1 to the power r to the power 6. So this is what is called as dispersion forces or London forces. Let me summarize once again. I have got two molecules. By themselves, they do not have got any dipole moment within themselves. By dipole moment, what I said, look out here. This particular molecule, ammonia, has got its own dipole moment. That means I can say the dipole moment of ammonia is in this particular direction. So it has a dipole moment by virtue of having an electronegativity difference between its constituent atoms. But out here, there is no such dipole moment. If there is no such dipole moment, then how do these particular two molecules comes and gets attracted towards each other? That's the question I'm trying to answer. So what is going to happen now, if you just kindly look at me, what is going to happen is like this. What is going to happen is like this. If you just kindly look at me. What is happening out here is these two molecules are rotating and they're coming close to one another. Now, as they're coming close to one another, one particular electron cloud is interacting with the electron cloud of the other molecule. These two molecules have now started to interact with one another, electronic clouds. Now, electrons, each of the electrons repel each other. So, as this electron comes out here, this particular molecule, the electrons of this molecule goes away out. That means electron density of the second molecule now becomes higher in this particular region. So delta negative. And the electron has shifted from here, that means this becomes delta positive. So the dipole moment will be directed in this particular direction, from positive to negative. Now, since this has become a positive center, as far as this particular molecule is concerned, the electrons will be dragged towards this particular positive center. That means the electron cloud will now come in this particular direction. So this will become delta negative. That will be delta positive. That means the direction of the dipole out here will be in this particular direction. That means I have got a positive center in this particular molecule, a negative center in this particular molecule. There will be a charge separation, attraction will be there. And that attraction is called essentially as the reason for this London forces. It's a very short range force. If I change the distance slightly, taking each of the molecules a little bit further from each other, this kind of attraction just vanishes. So this kind of attraction is only there when the two molecules are sufficiently close to each other. Right? How much? Maybe 500 picometers. 500 picometers means 500 into 10 to the power minus 12 meter. Only at this particular distance, the forces actually is operational. They are actually acting with each other. This is what we call as the London forces. Clear? Is that clear?
Yes, sir.
Shamsita, Rachel,
Yes, sir.
Aditya?
Yes, sir.
Yes, sir.
Fine. So this is what I call as force. Now, next one is rather simple. It's a dipole-dipole forces. These are called as dipole-dipole forces. Next one is what we call as dipole-dipole forces. Now, what does dipole-dipole forces actually means? It's very simple now. Right? Now, suppose I have got two HCl. Say, for example, I have got two HCl out here. I have got H, I have got Cl out here. Right? This one is delta negative. This one is delta positive. So I have got a negative center out here. I have got a positive center out here. And this is my entire molecule. And my entire molecule is this. But this is my entire molecule. I have got a delta minus center out here, H plus out here. Suppose. Now, I have got, once again, say for example, I have got another molecule out here, which is H and Cl out here. So I have got delta plus out here. I have got delta minus out here. In this case, the direction of the dipole is this. In this case, the direction of the dipole is this. Right? Now, look out here. Now, I have got essentially a negative center and a positive center adjoining to each other. I have got a negative center and a positive center adjoining to each other. So naturally, there will be attraction. So naturally, there will be attraction. That means this particular molecule will try to come as close as possible to this particular molecule. This kind of interaction is called as dipole-dipole interactions. It's very simple to understand. So any polar molecules, polar means which have got a dipole. Non-polar means which do not have got a dipole. So any particular polar molecule will be attracted towards each other, right? In such a way so that they are such a way because of the positive and the negative centers are adjoining to each other. Attraction, positive attracts negative. So all these molecules will be closely packed. They will be attached with one another. This is a kind of a dipole-dipole forces. It is not as short and range as that of the London forces. Here, attraction is proportional to 1 by r cube. That means it is a little bit far. That means out here, suppose for London forces, I need the molecules to be very close to one another. Only then the London forces is going to act against each other or on each other. But in case of dipole-dipole forces, the molecules can be a little bit farther away, but still the dipole-dipoles are going to interact with each other. So this is also short order, but not as short order as that of London forces. This is what is called as dipole-dipole forces. I've given you the example of HCl, right? Very good. Right. Did all of you understand this? Aditya,
Yes, sir.
Drisha, Regula,
Yes,
Yes,
sir.
sir.
Samstita, Samstita.
Yes, sir.
Chalo. So this is a dipole-dipole forces. Right? Now, then comes dipole-induced dipole forces. Dipole-induced dipole interactions or forces. Now, what does it mean? It essentially means, once again, very simple. Right? Suppose you have got one polar molecule. Say, for example, I have got one HCl out here. So this is delta minus and I have got delta plus. Suppose I have got this, right? And I say, for example, I have got a non-polar molecule, such as, say, for example, hydrogen, suppose. So I have got a polar molecule. I have got a non-polar molecule. Okay. Now, what happens is this, like this. Look, out here I have got an electronic cloud. This particular molecule has got an electronic cloud surrounding it. You have already done a little bit about molecular orbital theory in the last class. So this has an electronic cloud. Now this is delta minus. That means the electrons, when these two molecules are approaching towards another, you have got a minus side center out here, and you have got an electron cloud out here. You have got an electron cloud out here. This is my electron cloud. So what this is going to do is this, as they come closer to each other, this basically is going to interact with it. As a result, the electronic clouds, the electrons at this particular area is going to shift out here. That means this will now become my delta negative. Because the electrons are moving in this particular direction, these electrons are getting repelled by this delta minus. So these electrons will be moving in this particular direction. So if this becomes delta minus, then automatically this will become delta plus. That means the polar molecule, induces a dipole in this particular molecule. The polar molecule induces a dipole in this non-polar molecule. This is dipole-induced dipole. There, I have got a permanent molecule which have got a permanent dipole. It has got negative charge out here. Negative charge means electrons. This particular molecule also has got electronic cloud around it, surrounding it. When this particular molecule approaches this molecule, or vice versa, then this negative charge is going to repel the electronic cloud of this particular molecule. As a result, the electronic cloud out here is going to shift from this particular area to this particular area. And if it shifts, then this will be become delta positive. This particular area will be delta positive because the electron have shifted from here to here. And this will become delta negative because electrons have moved from here to here. Previously, it was neutral. Now I have got a delta positive center out here. I have got a delta positive center out here, and I have got a delta negative center out here. So there will be interactions between them, attractions between them. Now the question is this, why is this attraction rising? Because this particular dipole, this polar molecule, induces a dipole in this particular molecule, which was initially a non-polar molecule. So this kind of an interaction is called as dipole-induced dipole process. This was first devised, this was first found out by Dipole. So it is also called as Dipole interactions or Dipole process. Right? So three
Yes,
types of
sir.
forces. So three type of forces we talked about. Number one is London forces. So London forces is what? Non-polar interactions. What's the reason? Fluctuating dipoles. Then I have got polar interactions. Finally, what I have got is Dipole forces, which is polar non-polar molecules. Together, these three forces have got a name. They are clubbed together, and these three have been given a name called as van der Waals forces. They are called as van der Waals forces. These are the three different kinds of forces that we talked till now. Clear to all of you?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, fine. Now, I'll spend a little bit more time because you'll be requiring this a lot in your organic chemistry on the London forces, right? Because in organic chemistry, essentially, we basically talk about organic chemistry. Carbon-hydrogen bonds are essentially taken to be non-polar, even though there is a slight electronegativity difference. Carbon is 2.5, hydrogen is 2.2, even though there is a slight bit of electronegativity difference, till we take them to be non-polar. So whatever we are going to discuss is important for now and important in future too. Right. So we are going to talk about the London forces, the factors upon which London forces depends upon. We are going to talk about this. By the way, if you understand this is attractive. This is also attractive force. These are all attractive forces. They're all attractive forces. Till now, we have talked only about attractive forces. All of these forces that we talked till now are attractive forces. This is a very important point. So van der Waals forces are attractive forces. Right. Now, let me talk about the factors upon which it is going to depend upon. Number one is molecular size. Larger molecules will have higher magnitude. Magnitude of London forces. Simple. Can you explain why? Why was London forces actually was operating? Because the electrons were fluctuating across the nucleuses. So it was going in one particular direction, which was actually creating the electrons of the other molecule to repel. So plus minus was happening because of a fluctuating electronic cloud. Bigger the molecule, lower will be the attraction of the electrons towards the nucleuses. Easier will be for the electrons to fluctuate. So therefore, bigger the molecules, higher will be the London forces. Clear? So larger the molecules, higher will be the London forces. Yes or no?
एक बार वापस बता दीजिए ना.
लंदन फोर्सेस किस लिए हो रहा है बता पहले तो.
सर फ्लक्चुएशन
हाँ बोल. First of all, why London forces is taking place?
सर फ्लक्चुएशंस ऑफ इलेक्ट्रॉन्स
Electrons. Fluctuations of the electrons for what? From what? It is changing its shape. Yes or no?
यस सर
Fluctuations of electronic clouds. Now, if the electrons are tightly held, will the fluctuations take place or no?
नो सर
No. In larger molecules, are the electrons placed far away from the nucleuses of the molecule?
यस सर
Will the fluctuations be more now?
यस सर
Will the London forces be more now?
यस सर
That's the point. Larger molecules, lesser attraction between the electrons and the nucleuses, greater fluctuations, greater London forces. Clear? Clear, yes or no? Okay. Second point. Number of electrons. More the number of electrons, higher will be the London forces. Yes or no? Tell me why. Same as shielding, same as the food. 4 rasagullas are there, only Drishya is there. He's going to eat all 4. 4 rasagullas are there, and we 5 go out there. Drishya will get not even 1. More the number of electrons, lower becomes the attraction of the electrons towards the nucleus. Effectively, greater will be the fluctuations. Clear? Shamstita, Aditya, Rijula?
यस सर
Yes, sir.
Shamstita, Rijula? Rijula নেই নাকি?
হ্যাঁ স্যার
Rijula কোথায় গেল? রিজিলা কখন গেল রে? আমাদের সিস্টেমটা গন্ডগোল করছে বোধহয়। সংস্থিত तू रुक, मैं आ रहा है, ये मेरा सिस्टम गड़बड़ कर रहा है। आ गया, चलो। एक सेकंड, এই জিমি ফোনটা নিয়েছিল না, রিজুলাকে ফোনটা দিয়ে যাও।
দেখছি
দেখলে তো হবে না।
ওই ফোনটা কি হলো না ওই ফোনটা সব সেট করে দিও তাহলে আর তোমারটা নেবে না ওর কাছে যে প্রজেক্ট করে দিও সমস্যা অফ টাইম না তোমারটা নেবে না
ও নিজেই করুক, ও সব জানে। আচ্ছা আদিত্য, বোঝা গেছে এটা?
হ্যাঁ স্যার।
ওই তো রিজুলা এসে গেছে, ঠিক আছে। হ্যাঁ, তুই কোথায় চলে গেছিলিস? ঠিক ঠিক। আদিত্য বোঝা গেছে?
হ্যাঁ স্যার।
ঠিক আছে। নাম্বার 3, surface area of molecule. Higher the surface area, higher is the London forces. Can you explain this?
Sir, more area, more space for fluctuation.
Can you explain this? Say for example, I have got a molecule like this, and this molecule gets coiled in this particular area. Which one will be having a higher London forces and why? The same molecule. I have got this particular molecule, and I have basically coiled this particular molecule in this smaller shape. The same molecule. One is an elongated shape, and the same dimension, same size molecule I have coiled in this particular direction. Which one will be having a higher London forces and why?
Sir, the first one.
Why?
Sir, because the electrons can go extreme left, sir. ज़्यादा दूर जा सकता है.
Cut. Nothing. Electron extreme left, extreme right. These molecules have always electrons on the top of it. Yes or no? Electrons is along this particular molecule. Now what happens is this: if the electrons are all exposed, then when another molecule comes out here, there will be interaction directly between these electrons and these electrons. But out here, all the electrons are shielded within this particular shell. So even if this particular atom molecule comes, there will be less interactions because these molecules are inside this particular shell. Not to the left or not to the right. It is the number of electrons that are exposed to the outside stimulus. What is the outside stimulus out here? Outside stimulus is this, the incoming atom or molecule. Got it, Trisha?
Yes, sir.
Extreme left, extreme right कर रहा है. बड़ा देखा ना? भेज दिया. ठीक. Now I'll give you a small question out here. Then I'm going to discuss about hydrogen bonding. Explain the boiling points. Inorganic এটা ভীষণ ভাবে লাগবে. This is the boiling points. CH4, GeH4, SiH4. Boiling point order টা কর. Okay, let me just change this question a little bit. Let me change this question a little bit. Ascending order of boiling points. Good. I'll give you 2 minutes time. Look at the periodic table and then decide. Look at the periodic table. हो जाने से बुला ले, मैं सामने नहीं है. हो गया হয়েছে সংস্কৃতা রিজুলা আদিত্য दृश्य बता बता जल्दी बता
नो सर
नो सर संस्कृता
স্যার
No,
পাচ্ছি না
sir.
আমরা
রিজুলা
No,
আদিত্য
sir.
আদিত্য
স্যার পাচ্ছি না
আচ্ছা পিরিয়ডিক টেবিলে এগুলো সব কোন গ্রুপের রে which group does this belong carbon germanium silicon
14
yeah 14 10 12 13 14 14 তাহলে আমার প্রথমে কি আছে প্রথমে কার্বন আছে তারপর সিলিকন আছে তারপর জার্মেনিয়াম আছে ডাউন দ্য গ্রুপ আমার সাইজ বাড়ে না কমে
सर इंक्रीज
इंक्रीज यहाँ पर तो 4 ही हाइड्रोजन है चारों का इसको तो साइज बराबर तो CH4 का साइज क्या होगा छोटा सिलिकॉन SiH4 का साइज और बड़ा होगा जर्मेनियम को साइज और बड़ा होगा तो किसको बीच में लंदन फोर्स ज्यादा होगा
सर जर्मेनियम
मॉलिक्यूलर साइज आदित्य বোঝা গেছে
হ্যাঁ স্যার
শক্ত সংস্কৃতা শক্ত ছিল না সোজা ছিল সংস্কৃতা
না সোজা ছিল
রিজুলা
হ্যাঁ স্যার
বারবার করে বলছি একটু পড়াশোনা কর নালে কিন্তু খুব মুশকিল হয়ে যাবে তার মানে আমার CH4 এর বয়লিং পয়েন্ট will be less than that of SiH4 which will be less than GH maximum এটা minimum এটা clear now
Yes, sir.
what we are going to do is another kind of very special kind of bonds which have got huge significance in chemistry. This is very, very important and you can be sure that you'll get questions from this particular section in your class tests, half yearly, as well as your end terms. This is called as hydrogen bonds. Hydrogen bonding. Now, hydrogen bonding usually takes place with predominantly with only three atoms. What? One of them is nitrogen, the other one is oxygen, and the other one is fluorine. These are the predominant atoms involved in hydrogen bondings. Right? Chlorine is also there to some extent. I'll explain. Now, what is common between all these three? Very high electronegativity. This has got an electronegativity value of 3. This has got an electronegativity value of 3.5. This has got an electronegativity value of 4. And this has got an electronegativity value of 3.2. I told you again and again, you have to understand periodic table. You have to remember the electronegativity series. Otherwise, even if you understand everything, you cannot do any questions. Fine. So, what is hydrogen bonding? Suppose I have got a particular molecule, say HCl, or say, for example, HF. Right? Now, F has got an electronegativity value of 4 and hydrogen has got 2.2. So this will be my delta minus and this will be delta plus. Similarly, out here, I have got H and F. I have got delta plus. I have got delta minus. So between these two, there will be a hydrogen bonding because you have got a minus charge out here. You have got a plus charge out here. Since fluorine is very electronegative, therefore, it has dragged a lot of electrons from this bond pair towards itself. So it will be substantially delta negative. Since it has dragged a substantial amount of electrons towards itself, there will be a substantial deficiency of electrons in H. So it will be substantially delta plus. So there will be a strong attraction between this delta minus and this delta plus. This is called as hydrogen bonding. There is no such physical sharing of electrons. No. This bond involves only electrostatic attractions. Then comes, say, for example, water. Let's talk about water. So water has got a shape. If you go into the hybridization, water has got a shape like this. This is 3.5, this is 2.2. So this will be delta minus and this will be delta plus. Now out here, what you will be having, you have got another water out here. So out here, this will be delta minus and this will be delta plus. So is दोनों को बीच में, there will be hydrogen bonding. There will be hydrogen bonding in between these two. There will be hydrogen bonding out here. Similarly, you can have another particular molecule out here. You have got O, you have got H, you have got H. This is also delta negative, this is also delta positive. So out here also there will be substantial hydrogen bonding. That means what they do hydrogen bonding is they make an associated structure. What they do is associated structure. Right? And when you have got this associated structure, suppose if you want to break these molecules into gaseous state, say suppose for boiling, you need to separate this particular molecule from this particular molecules. You have to separate all these molecules from each other. In boiling is gaseous state. That means all the molecules are independent. That means you have to break all these bonds. Similarly out here, not only here, out here what you will be having, you'll be having out H out here, you'll be having O out here, you'll be having out H out there. Once again, there will be a hydrogen bonding between this. So you have to break all these strong electrostatic attractions towards each other. That means the boiling point goes on increasing. You can be absolutely sure in some form or other form, you will be getting questions on hydrogen bonding in your class test, in your mid semester, in your end semester, always. It's one of the most important concepts as far as chemistry is concerned. Who can form? Look, I require for a substantial delta positive and delta negative to happen, very electronegative elements. So essentially, hydrogen bonds are formed by compounds which do not only have hydrogen, but also have nitrogen, oxygen, and fluorine. That means ammonia can also form hydrogen bonding. HF I have shown, water I have shown, all of them, they have got one thing common. They have got hydrogen and an electronegative element. And when I've got a hydrogen and an electronegative element, what's happened is this. Just because the element is very electronegative, it drags a lot of electrons from hydrogen towards itself. So it becomes substantially delta negative. And since a lot of electrons has been taken, but a lot of concentration or density, electron density has been taken away from hydrogen, hydrogen will become delta positive. So the same story is applied for one molecule, and the same story is also applicable to all the molecules in that particular sample. So I have got a lot of positive charges and a lot of negative charges in that particular sample. So there will be a bond formation. What kind of a bond? Electrostatic bond. And what is the energy approximately of hydrogen bonds? It can vary between 10 kilojoules to 100 kilojoules. And this is a lot of energy. So hydrogen bonds, many phenomena in chemistry, as we'll slowly understand. You're just beginning chemistry, right? It's just maybe the third month that I'm teaching. Or maybe, yes, it's the fourth month, I guess. First, fourth, or third, I don't remember. So you'll understand that lot many phenomena are going to depend upon hydrogen bonding. One of them is boiling point. Why the boiling point of water is so high? They might very well ask you. So only 4 atoms: nitrogen, oxygen, fluorine, and chlorine. They are the only one which can form hydrogen bonds. Clear?
Yes, sir.
Samstita, Rijula, Aditya?
Yes, sir.
Yes, sir.
Yes, sir.
Sure. So what we have done right now is we have talked about 4 different kind of interactions that takes place between individual molecules. We're talking about molecules, mind it, not atoms. We're talking about molecules. Number 1 was Debye forces. The second one was dipolar interactions. The third one was London forces. Together, these 3 forces, Debye, London, and dipolar, are called as van der Waals forces. What kind of interactions? Attractive. Then we came across hydrogen bondage. What kind of interactions? Attractive. So the point is this, that in a sample consisting of molecules, there will always be attractive forces operating. Polar, non-polar, really doesn't matter. If it is polar, the attraction will be stronger. If it is non-polar, the attraction will be there. The attraction will be small. But nevertheless, every single molecule will feel attraction towards other molecules. Due to what? Due to van der Waals forces. Due to what? Due to van der Waals forces. That's the summary of that entire story that we have been talking for the last 1 hour, 10 minutes or so. Right. Now, coming to gas laws. Now, the gas laws are the simplest one that we can possibly discuss. Why? Because in gas laws, the attractive forces are nominal. The attractive forces are nominal. How do we know that the attractive forces are nominal? Very simple. If you put a particular gas in a particular room, suppose you spray a little bit of room freshener at one corner of your room, and you are sitting somewhere far away, within a few seconds, you are going to have that beautiful fragrance coming to you. Why? Because it has spread. Because the gas consisting the fragrance molecules have spread. Why did it spread? Because there's no attraction between them. That's why they're free to roam. They're free to roam. That means the attraction between the molecules are nominal, if at all there is. What I'm trying to say is this. Suppose this is my room. And out here, I am spraying this number of gaseous molecules out here, which have got a beautiful smell. And Shamsita is sitting down in the chair, sleeping on the table. Now, within a few fraction of seconds, she smells beautiful smell. Had the molecules are attracted towards each other, that means they would have been together. they would have been together. One molecule will not go simply in different directions. Just because Shamsitas you smell almost immediately, that means this molecules, one particular molecule of the gas and the other particular of the molecule of the gas have got no attraction towards each other, nominal, if at all. So what I was trying to say is this: amongst all the systems that you need to study, the gaseous state, the liquid state, the solid state, the liquid state and the gaseous state will be the next year, second in class 12. In this case, we have got just the gaseous state, right? In this cases, the forces of attractions are nominal, and therefore it's very simple to treat. Very simple to treat. It depends only upon 4 parameters. It depends upon pressure, it depends upon volume, it depends upon temperature, and it depends upon the number of moles. That is the mass. So you can define a gas by just explaining through these 4 parameters. You don't have to bring any other particular concept of attractions between molecules. There's no attraction, is there? You don't have to write down an expression for repulsion between the molecules. There's no repulsion. That means there's no interaction or nominal interaction. That's why nominal interactions. Right? For gases. That means they're very simple to treat. And our chapter, essentially, which we have started today, we are going to talk about the different laws the gas laws follow, irrespective of its nature. I can take hydrogen gas. I can take nitrogen gas. I can take methane gas. I can take oxygen gas. Really doesn't matter. All the laws are valid for all the gases. So therefore, it's very simple. Right. Now, there's another thing that you need to know, which is called as thermal forces. So when we talk about van der Waals forces, or when we talk about hydrogen bonds, gases, by the way, do not have got hydrogen bonds. Usually they do not have, except carboxylic acids, right? They are all attractive. They're all attractive forces. Now, what is thermal force? Let me explain this. Thermal forces essentially, say for example, is the room temperature. Suppose you say that what is the temperature? You say today is very hot. What do you mean by saying that today is very hot? Oh, sir, it's very hot, it's 35 degrees centigrade. Okay, fine. What do you mean by 35 degrees? It's a measure. Measure of what? What do you mean by thermal forces? What do you mean by temperature? It's a measure of what? You say heat. What do you mean by heat? You are asking too many questions. Don't ask. I don't know. I use this term 1,000 times in my life, but I don't know what is heat. Okay, fine. I understand. Okay. What's happening is this. Right? Suppose you have got air molecules. These are my air molecules. Suppose these are my air molecules. They are very small molecules, gaseous molecules, very small molecules. And they are moving in all possible directions. They are moving in all possible directions. Okay. Now, why they're moving? Anything that moves has got energy. So that's why they're moving. So when you say talk about a room temperature, it means that the gaseous molecules in this particular room are moving at a faster rate than if the temperature was low. Because higher the energy, faster will be the molecules moving, but higher will be the energy. Energy means what? Somebody has to absorb the energy. Energy cannot stay in vacuum. So who is absorbing the energy? The energy is being absorbed by the gaseous molecules. If the gaseous molecules are absorbing energy, what are they going to do with that extra energy? They're going to move faster. The energy will be higher. They are going to move faster. Right? So they are moving faster in all possible directions. Some molecules are moving in this direction. Some molecules are moving in this direction. So all possible directions they are moving. So total random forces. So they are basically moving in random directions. Now this gas also have got mass. They also have got a mass. They have got a velocity. Therefore, they have got a momentum. And therefore, they have got a force. They're moving. The gas molecules have mass. They have got velocity. They have got momentum. And therefore, they have got a force. And the forces that these particular molecules are exerting, say, for example, on my gaseous system that I am considering, they're attracted towards each other. Or any, say, I can talk about solids, I can talk about liquids, I can talk about gases, anything. My experimental system, they consist of molecules. So they are getting attracted towards each other. Why? Maybe due to van der Waals forces, maybe due to dipole-dipole interactions, maybe due to hydrogen bonding, maybe due to whatever it is, they're getting attracted. Now, this particular molecule is facing collisions from the molecules surrounding it. They're colliding. And while they're colliding, they're supplying energy to these gaseous molecules. This particular system that we are considering, our system is this. Our systems are this. I've taken only two molecules. Now, within these two molecules, what I've got a force of attraction. And what is this particular molecule trying to do? They're giving energy to it. If this amount of energy is greater than this amount of energy, the attraction, that means this is going to do random forces. They're going to hit. So whatever, once this basically tries to hit, what is going to happen? These two molecules are going to gain energy. If they're going to gain energy, what will they try to do? They will try to move. I'm giving energy. The energy is increasing. They will try to move. If they try to move, and if they are able to move, they will go further from each other. So this attraction is broken. So you see that this gaseous molecule, the thermal energy, right? Or the molecules in a liquid, whatever it is, the energy of the surrounding molecules. Say, for example, I am the system. Say, for example, I am the system. And the molecules are hitting me from all possible directions. They're slapping me, they're kicking me from all possible directions. But I'm still intact. I'm not breaking down. Why? Because the attraction between the molecules of my body is higher than that of the disruptive forces given by the surrounding molecules. So I remain a rigid structure. I remain a solid structure. Nothing is going to break. If, however, the thermal energy can break it easily, the molecules are going to move in all possible directions. And that's why Schongstetter, while sitting down at the corner, is going to get the smashed fragments. Because the molecules of the gas, of the atmosphere, the molecules of the air, the molecules of the atmosphere is good enough to break the van der Waals attraction of the fragment molecules. And that's why these two molecules get separated and goes to Schongstetter. And she gets the smell and wakes up from a slumber. So, if thermal forces can break down the forces of attraction, it will be a gas. If the thermal forces can make a little bit of movement possible without breaking down completely the bonds, it will be liquid. If the thermal forces cannot do anything, cannot move the molecules from each other at all, you will be getting solid. So my thermal forces are essentially nothing but disruptive forces. So if the disruptive forces are greater than the attractive forces, the system is going to break down into different individual molecules. Sugar takes a lot of time if you want to basically do what? If you want to basically try to mix it with a spoon. Heat the water a little bit, immediately it dissolves. What happens? When you're taking the sugar, as such, it is solid. That means the forces of attraction between each individual sugar molecules is substantial at atmospheric room temperature. That means it's not breaking. Put it into water, slow, heat a little bit faster. While you are heating it, what's happening? The water molecules are basically moving at faster rate and is going to hit the sugar molecules at a faster rate. The randomizing force, the disruptive forces now becomes higher than the attractive forces. Sugar immediately dissolves. These forces, these randomizing forces, these disruptive forces are called thermal forces. And the interaction between these thermal forces and the disruptive forces will actually tell you whether a particular matter will be solid or liquid or gas. Is that clear to all of you? If not, please tell me. Is that clear to all of you?
Yes, sir.
Translator? Translator?
Yes, sir. Yes, sir.
Yes, sir.
Rijula Aditya?
Yes, sir.
বোঝা যাচ্ছে না কিছু বোঝা যাচ্ছে না?
Yes, sir.
আদিত্য? বোঝা যাচ্ছে আদিত্য? আদিত্য?
Yes, sir.
বোঝা যাচ্ছে?
Yes,
বোঝা
sir.
যাচ্ছে কি যাচ্ছে? ঠিক আছে. Now you see, suppose you have got a gas. You cool it down. Sometimes, as we'll see later in this particular chapter itself, when we talk about liquefaction of gases, it will basically, when you cool it down, right, or give high pressure, let me just talk about cooling it down. It will transform into a liquid. Why? While you're cooling it down, that means you are basically decreasing the disruptive forces. You are decreasing the disruptive forces. That means you are allowing the two molecules of the system I'm considering to come in close contact with each other and fall into the trap of attractive van der Waals forces. And they stick together with one another. But still they're moving. They are within the van der Waals forces. But the van der Waals forces is allowing them to move a little bit from here and there. That's why a liquid flows. It has got no shape, fixed shape, but it has got a fixed volume. Cool it further down. That means the disruptive forces you are decreasing further. No disruption at all. That means now these two molecules will come closer to each other because there's no other force to disrupt them. They will come in close contact with each other and remain as such. It will become solid. So essentially, a gas, liquid, and solid are nothing but different states of matter. And that's why you have used the word states of matter, maybe from your class 9th standard. The same matter, different states, solids, liquid, and gas, because it is an interplay of the attractive forces vis-a-vis the disruptive thermal forces. Clear? Bishop?
Yes, sir.
Yes, sir.
Okay, now I suggest all of you, I think I had enough today. These are very difficult concepts. I want you to read the NCERT book. At least I covered 5 or 6 pages today. Up to this particular point, along with you are going to read the Boyle's law. Write it down in a notebook. Sunday. So I've got a couple of days out here. Today's Wednesday, Thursday, Friday, Saturday. You've got 3 complete days. You are going to read the Boyle's law, the Charles law. Just read it. Explaining is my responsibility. The Boyle's law, the Charles law, the Avogadro's law, and the Gay-Lussac's law. Next day, we plan to complete at least these 4 laws because there's nothing out there except understanding those graphs. These are all experimental observations. Let me give you a small hint. These are all experimental observations. It has got no scientific validity. It has absolutely these are experimentally, we have observed it. And we have seen that almost all the gases behaves in a similar way. And therefore we call it as a law. That's why we call it as a law. All you need to do is this. How is pressure varying with volume? How is volume varying with temperature? How is volume varying with, say, for example, pressure varying with temperature? Gay-Lussac's law. How is volume varying with mass? Avogadro's law. So there's nothing. These are all experimentally observed quantities. So there's very little to teach in that this particular point, whatever I did today required a little bit of explanation, not much, but required a little bit of explanation. But whatever I'm going to do next day, of course, I'm going to give you basically explain those graphs. Graphs is the only part where you require a little bit of teacher's help. Otherwise you don't. So I intend to complete all those 4 laws at least for the next day. And then one day I'll be requiring for van der Waals gases, and the other day I'll be requiring for liquefaction of gases. So I'll be having another 3 lectures in which I intend, that is by next Sunday. By next Sunday, I intend to complete gas laws, if you kindly cooperate with me. So Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's law. Kindly read this 4 and come in the next test class, so that I can be a little bit faster, because this is the month of November. Most likely you'll be having your exam in the month of March. So hardly I have got December, January, February. Anyway, we started very late. I don't know how much I'll be able to complete. So inorganic chemistry, most likely I will not be able to do anything. I would suggest you to do a lot in class 12. But what I'm going to do is this, I'll explain inorganic chemistry. Because by March, I don't think I'll be able to complete. We are pretty slow and we started very late actually. We started in the month of, I guess, June or July. So that is almost 4 months later we started. Songstead, of course, started a month earlier. So inorganic chemistry.
নেক্সট পরীক্ষা সিলেবাস দিয়ে দিয়েছে।
কি আছে?
প্রথম চ্যাপ্টার গুলো নেই, এই চ্যাপ্টারটা কেমিক্যাল বন্ডিং আছে, তারপরে 3টে চ্যাপ্টার আছে।
গ্যাস লস আছে আর
পি ব্লক এলিমেন্ট আছে,
ওটা পড়ে নে তুই।
আর একটা মাঝখানে চ্যাপ্টারটা ভুলে যাচ্ছি।
কেমিক্যাল ইকুইলিব্রিয়াম নেই?
হ্যাঁ, ওটা নেই, মানে পরপর 4টে চ্যাপ্টার আছে।
পরপর 4টে চ্যাপ্টারের মধ্যে তো গ্যাস লসের পরে তো কেমিক্যাল ইকুইলিব্রিয়াম আছে।
হ্যাঁ, ওটার নামটা ভুলে গেছিলাম, কি ওটার পরে আছে পি ব্লক এলিমেন্ট।
স্যার
থার্মোডাইনামিক্স নেই?
হ্যাঁ, এটাও আছে।
কবে পরীক্ষা তোদের?
জানি না, ওটা বলেনি।
তবু কবে নাগাদ হতে পারে?
ডিসেম্বর।
মুশকিল বাবা, কি করে করবো আমি জানি না। তোদের প্রত্যেকটা লাইন পড়াতে হয় না, সেটাই তো মুশকিল আমার।
স্যার ইনঅর্গানিক কেমিস্ট্রি কোন চ্যাপ্টার দিয়ে শুরু হচ্ছে?
হাইড্রোজেন।
ঠিক আছে।
হাইড্রোজেন আছে, অ্যালকালি মেটালস আছে, এগুলো পড়, তো এগুলো বসে বসে পড়, সবাই এগুলো বসে বসে পড়, এগুলো আমি পড়াবো না, কিন্তু সময় পাবো না আমি। না, আমার পড়াতে কোনো অসুবিধা নেই। আমরা এত দেরি করে শুরু করেছি, কখন শেষ করবো আমি জানি না, এত স্লো আমরা। হ্যাঁ বল, কি क्या दृश्य बोल, क्या बोलना चाहते हैं?
सर वो स्टोइचियोमेट्री का क्लास
देखते देखते हैं बेटा।
স্যার বেসিক্যালি সেকেন্ড বইয়ে ইনঅর্গানিক কেমিস্ট্রি আছে।
এই রিজুলা রিজুলা বলছি, রিজুলার কাছে তো থাকার কথা। আচ্ছা, সংস্কৃত তোর কাছে কি স্টয়চিওমেট্রি ক্লাসটা কি লেকচার গুলো আছে তোর কাছে?
হুম
না
হুম।
উড়িয়ে দিয়েছিস?
না, আছে আছে।
ওদেরকে একটু ভিডিওটা পাঠিয়ে দে তো গ্রুপে।
ঠিক আছে। আর স্যার বলো না, সেকেন্ড বই থেকে শুরু হচ্ছে নাকি?
সেকেন্ড বইয়ে তো পি ব্লক শুরু হচ্ছে, ওই ইনঅর্গানিক আর ইয়েটা আছে, ইনঅর্গানিক আর অর্গানিকটা আছে।
सर मेरा तो ये सारा सब एक साथ आ रहा है थर्मोडायनेमिक्स पी ब्लॉक एलिमेंट एस ब्लॉक एलिमेंट्स
সেকেন্ড বইয়েই তো লেখা আছে স্যার।
এটা আপনি
সেকেন্ড
কি,
বইয়ে লেখা আছে অর্গানিক কেমিস্ট্রি বেসিক প্রিন্সিপাল টেকনিক্স।
হ্যাঁ ওটাও আছে, তার সাথে এটাও আছে, ইনঅর্গানিকটাও আছে। ফার্স্ট বই খালি ফিজিক্যাল,
হাইড্রোকার্বন।
ফার্স্ট বই খালি ফিজিক্যাল কেমিস্ট্রি, গ্যাস লস, কেমিক্যাল ইকুইলিব্রিয়াম আর আয়নিক ইকুইলিব্রিয়াম দিয়ে শেষ ফার্স্ট বইটা, থার্মোডাইনামিক্স। মানে ফার্স্ট বই শেষ করতে এখন আমাদের 4টে চ্যাপ্টার। তারপর আমি ইনঅর্গানিকটা তো দেখে করাবো না, অর্গানিকটা আবার পুরো ডিটেলসে করাতে, অর্গানিকের জন্য 1.5-2 মাস লাগবে আমার।
ও এই ব্যাপার।
অনেক দেরি করে শুরু করেছি না। না বল দৃশ্য, কে বললো চাপে?
नहीं सर कुछ नहीं
Started late better, how can I you tell me which chapters you want to do, I can do those chapters. But if you tell me to do complete the entire syllabus what were after 4 months, I cannot do it.
नो सर बाकी हो जाएगा मेरा
ठीक ठीक ठीक, कैसी होगा
बस एक
बेटा?
थर्मोडायनेमिक्स का चाप है
थर्मोडायनामिक्स तो चाप है ही, थर्मोडायनामिक्स भी चाप है, केमिकल इक्विलिब्रियम भी चाप है, आयनिक इक्विलिब्रियम तो बहुत ही चाप है।
नहीं सर वो इक्विलिब्रियम नहीं आ रहा है मेरा
ना नहीं आ रहा है, अभी तो आएगा ना, दिसंबर मार्च फरवरी मार्च में तो एग्जाम होगा तेरा।
यस सर तब आएगा
कितना दिन और बाकी है बता? माने आई कैन हार्डली डू, माने मे बी 2/3 ऑफ योर सिलेबस। इनऑर्गेनिक में नहीं करेंगे, नहीं कर पाएंगे। इनऑर्गेनिक आप लोग खुद कर लो। রেজুলা শুনছিস?
হ্যাঁ স্যার।
নিজেরা পড়, কোথাও আটকে গেলে আমাকে জিজ্ঞেস করে নিবি প্রশ্নগুলো। অর্গানিকটা একটু তোদের বোঝাতে হবে, অর্গানিকটা তোদের বুঝতে অনেক সময় লাগবে। অর্গানিক উই ক্যান স্টার্ট ইভেন নাও, কারণ আমার ওই কেমিক্যাল বন্ডিং চ্যাপ্টারটা শেষ হয়ে গেলেই অর্গানিক আই ক্যান স্টার্ট। এই যে থার্মোডাইনামিক্স কেমিক্যাল ইকুইলিব্রিয়াম লাগে, অতটা লাগে না কিন্তু।
স্যার পাঠিয়ে দিয়েছি
কাদেরকে?
তোমাদেরকে।
স্টয়চিওমেট্রিটা পাঠিয়েছিস তো?
হ্যাঁ সব পাঠিয়ে দিয়েছি।
ठीक ठीक, दृश्य देख ले एक बार, स्टोइचियोमेट्री वाला दृश्य
हाँ सर आ गया
एक बार देख ले, वहां पर अटक जाएगा तो मुझे पूछ लेना,
ओके सर
ठीक है? एक ही तो चीज पर आएंगे,
यस सर
अगर तू कहां पर अटक जाएंगे, सर ये जगह समझ में नहीं आया, वो जगह समझ में नहीं, तो आई कैन एक्सप्लेन यू, ठीक है?
ओके सर
आदित्य तो को
Yes,
बोल रहा
sir.
हूं, तो आदित्य তুইও তো স্টয়চিওমেট্রি করিস নি। আদিত্য, আদিত্য মাইক্রোফোন বন্ধ আছে তোর, ठीक है? सो व्हाट वी आर गोइंग टू डू इज दिस, आई एम गोइंग टू बेसिकली, तो पढ़ के आने से जल्दी हो जाएगा। आप लोग पढ़ते नहीं हो ना, एवरीथिंग आई हैव टू टीच ना, उठाई तो मुश्किल होएगा चला। ठीक है चलो, नेक्स्ट डे, बाय, गुड नाइट।
बाय सर
বাই।
রিজুলা, আদিত্য, টাটা।
হ্যাঁ স্যার টাটা।